Right, okay. Hello, anybody and everybody that's watching. Okay, cool. My audio is all fine. Nice. So, yeah, I had to, every time I change scenes between certain scenes, for some reason, I have to restart the stream. I don't really understand why, but if I don't, the audio kind of goes mucked up and I'm lazy, so I haven't really fixed it. I've just found a very low effort workaround, which is to end the stream and restart it immediately. So I'm being very lazy about it. Um, But anyway, so today I want to talk about black holes a little more. We spoke about black holes a little while ago. Well, if any of you were there when we spoke about black holes last, we talked about what did we talk about? We kind of looked at some GR and looked at the kind of time dilation properties of black holes. Very sort of classical stuff to do with black holes. And I guess we did some other GR stuff when we looked at Mercury's perihelion precession around the sun. This was also using this Schwarzschild metric, which it describes the sun in terms of general relativity, the gravity of the sun, but it also describes the gravity of black holes just fine. But what I want to talk about today is a little bit less classical, and is some slightly more contemporary stuff, though still not too contemporary. We're still talking like sort of the 1970s really for most of this, that describes the entropy and temperature of black holes. So this is a very interesting thing because it's the first real time that people managed to bring together in some way general relativity, that classically describes black holes and describes gravity, and quantum field theory, which describes particles and how particles really are better thought of as excitations of fundamental fields. Now, in what I'm going to do today, we're not really going to do any quantum field theory stuff. What we're going to do is we're going to kind of fudge a lot of it, but there's a very fudgy way to try and get the temperature of a black hole, and there's a slightly less fudgy way. So I'm going to do both ways. I'll do the very fudgy one, which is really quite underhanded, and then we'll do the slightly less underhanded one, which does use a little bit of relativity. Well, I mean, a little bit of tiny bit of general relativity, but not even really, actually. It's mostly just special relativity. You can think about it with really. And I've got a nice picture of a black hole up here, you can probably see. This particular black hole is supposedly Sagittarius A star. That is the supermassive black hole at the center of our own galaxy. And I think it's quite pretty. If you zoom out, you can see the accretion disk very nicely and the jets that are formed due to this accretion disk. But of course, the main interesting part is the closest in bit here, the very comparatively small bit compared to the rest of the accretion disk, but the horizon and within that, the singularity. These are the bits I think are most interesting. So they're the bits really that we'll be focusing on in some way. So I thought what I would do as well is what I've tend to have done in the past is I've sort of written down notes that I want to go through. So I've kind of worked things out in advance. And then I've sort of just basically rewritten them during the time when I'm streaming. But I think what I might do actually is I might just go through the things I've written up in advance and kind of talk through them. That way there's no kind of lag between me saying something and writing it down. And if you want to look at these notes that I've written up, that I've scribbled up, if you can actually read my handwriting, you can find them on my website. So if you go into my about section just below and you click on where it says website, then it's the tab that says Twitch office hours, and it's just right at the bottom where it says black holes and thermodynamics, and those are the notes I'll kind of be going through, or the things I'll be talking about that I've written down earlier. Okay. So the first thing you can probably see is that I've listed some useful reading. So some things I found very interesting to read while I was thinking about this. And the top one is a great thermodynamics book that I used when I was first studying thermodynamics. because I'm going to basically use this slightly as an excuse to talk a little about statistical mechanics and thermodynamics, because those are topics I really like. Let me turn my camera down a tiny bit. So for those sort of things, Blundell and Blundell's book is really, really good. I was actually taught by both Blundell and Blundell. The first, well, I don't know which one is first, which one is second in the title of the book, but the female Professor Blundell for relativity in my first year, and the male Professor Blundell for quantum mechanics in my second year. So my book is signed by, not both of them, but it's signed by one of them, by Stephen Blundell, which was quite a nice geeky moment getting him to sign it. And then the other one is this famous paper by Bekenstein. Now, there are a few papers by Bekenstein about black holes and entropy from the 70s, but one I thought was quite nice was this one from 1972, where he sort of sets out the argument that the entropy of a black hole should be associated with its area. Have I come across Finn's thermal physics? No, I don't think so. Not to my knowledge, I haven't. I've used Landau and Lifshitz, some of their stuff for thermal physics, and then Blundell and Blundell. Those are the only textbooks I've used for thermal stuff, really. Landau and Lifshitz is very good for statistical mechanics. I mean, it's good for pretty much everything. It's just quite heavy, but for statistical mechanics, I found it particularly insightful. Okay, so let's get going, I guess. So the first thing, before we start talking about black holes and thermodynamics of black holes, I think it's good to just look a little bit about thermodynamics in general and statistical mechanics in general. Hello to you too, Rooster. Thank you for saying hello. So before we get started, well, in getting started, I want to talk a little bit about microstates and macrostates in thermodynamics. So a macrostate is something that describes the system on a sort of a large scale. It's a large scale property of the system. If you think about gases in classical thermodynamics, macroscopic properties are things like temperature, volume, pressure, charge, and other things like that. So the state for the macrostate a system is in is something that is labeled by these overall properties of the system, these large-scale properties like temperature, volume, and pressure. It doesn't really know anything about what is going on on a much more zoomed-in scale. Okay. Ooh, swirlies. Oh yeah, that is the accretion disk. Hello, non-dairy neutrino. So that is what we'll take for our meaning of macrostate. It's the state a system is in described by these large-scale properties like temperature, volume, and pressure. Oh yeah, I did make you a VIP. I went through a bit of a splurge just assigning roles to people that I know had been in the stream a bit. So yeah, you have the honor of being a VIP. So in contrast to a macrostate, the microstate is the configuration and a very zoomed-in scale. A really nice analogy, I think, that is in the book by Blundell and Blundell is that if you imagine you've got a box full of coins, and you kind of shake this box about, so all your coins are flipped over, some are in heads, some are in tails. The macrostate of this system is just a description of, how many coins are on heads. But the microstate of the system would be the sort of exact labeling of which coin has a heads, which coin has a tails, and keeping track of all of the coins individually. So you can think about probabilities in terms of microstates. So the system, each macrostate of the system, so a macrostate in this example with coins is how many coins are heads. Then of course, conversely, the total number of coins minus the number that are heads is the number that are tails. So we only really need to specify which ones are heads. So the macrostate is the total number that are heads. But for each macrostate, there are lots of different possible microstates. If you imagine you've got 10 coins labeled 1, 2, 3 all the way up to 10, you could have 5 of them being all heads, but of those 10 coins, you could have any 5 being heads. You could have coins 1, 2, 3, 4, 5 being all heads, or you could have 6, 7, 8, 9, 10 all heads, or 1, 10, 9, 8, 7 all heads, and so on. And the system sort of will pick which macrostate to be in, the most likely state it will pick to be in is the one that corresponds to the most microstates, which sort of makes sense. It means there are the most possible ways you could arrange the system such that it is in this particular state. So for coins, these coins in a box, if you shake them around, of course, the probability of a coin being heads or tails is 50-50. So the most likely arrangement of coins in this box that you've shaken about is to have half of them as heads and half of them as tails. And you can explain this purely in terms of probability, or in terms of likelihoods, rather. The number of combinations of having 5 coins that are heads and 5 coins that are tails is drastically larger than having, 20% heads or 80% tails. So what you can do is you can write down an expression for the number of different ways of having some proportion of heads and some proportion being tails. And then if you maximize this expression, using a bit of calculus or something, you find that the maximum number of ways your system can be in a certain state is if it's roughly half, if it's half divided between all of the coins being heads and all of the coins being tails. You love entropy. I love entropy too. Exactly. This is basically just an excuse to talk about statistical mechanics. The black hole part is, well, no, actually, I was going to say the black hole part is the less interesting part, but actually, the black hole part is also quite interesting. Okay, so this is what we mean by macrostates and microstates. So, for example, as another example, if you've got a gas of particles in some isolated sealed container, you can measure the volume of this container, using a ruler or something. You can measure the pressure on the walls with some, I don't know, some sort of sensors, or seeing how much you have to hold the walls in to stop it flipping. You can measure the pressure in some way, and you can measure the temperature of the gas inside with a thermometer. So these are all macroscopic measurements. So this can help you describe the macrostate of the system if you know its temperature, pressure, and volume. So if you know all 3 of those things, you've sort of completely specified the macrostate the system is in. Whereas the microstate, you now have to think about sort of zooming in and looking at these individual particles. The microstate would correspond to a complete understanding of what each particle is doing, where it is, how fast it's moving, and so on. Okay, so there are lots of different possible microstates that will give you the same macrostate of some temperature, some pressure, and some volume. But, if you think, the temperature won't change if you swap the velocities of 2 particles, because the average kinetic energy, which corresponds to the temperature, is still the same. You've just sort of relabeled your particles, and the system doesn't care how you label particles. Okay, so there are lots and lots of microstates for a single macrostate, as I say here. So through kinetic theory, like I mentioned, we understand temperature roughly as being the average kinetic energy per particle in the gas. And there are lots of different ways we can distribute the velocities between these particles to give us the same average temperature. So there are lots and lots of microstates for a particular macrostate in this system of a gas. So entropy now is roughly a measure of how many microstates there are for a particular macrostate. Of course, if you have lots of different possible macrostates, then you have to think about the total number of microstates for each macrostate as well. But roughly it's a measure of how many different possible zoomed in configurations you're allowed for a particular zoomed out configuration. So, in a gas that has a particular temperature, pressure, and so on, the entropy is kind of a measure of how many different microscopic configurations there are. So ways of distributing your velocity between the particles to give the same temperature. That's a measure of the entropy of this gas. So a nice description of it is it's kind of like the ignorance you have of the system, of the particular microstate the system's or of the particular microstates that describe or that give rise to the macrostate the system is in. So for the very simplest thermodynamic system you can have, which is where the energy is totally fixed, this is sometimes called the microcanonical ensemble. It's a system that has a fixed total energy, like, you know, a totally isolated gas that has been had, where the gas molecules have had some temperature and it's been totally isolated from any surroundings. It can't lose any heat and it can't gain any heat. That would be an example of a microcanonical ensemble, something that has fixed total energy. So for this system, the entropy with dropping factors of Boltzmann's constant, because I'm not too bothered about that for now, is just given by the logarithm of the total number of microstates that are in that particular macrostate. So if you have lots and lots of different microscopic configurations that could form this particular macroscopic configuration with a fixed energy, then you'll have a lot more entropy. Okay, so the more microstates you have, the more entropy you have. Because the more uncertainty, the more sort of disorder you have, the more ignorance you have about what state your system is in. If there are lots of microscopic possible states it could be in, it's very difficult to say which one it is exactly. And there are different thermodynamic ensembles. So for more complicated systems where you don't have a fixed total energy, instead you might have a fixed temperature. So this would be like a sealed container of gas, where instead of totally thermally isolating your gas system, you kind of put it in a heat bath that has a fixed temperature. So it's allowed to exchange energy with this heat bath. It can gain some energy, or it can lose some energy, you know. And this stuff is sort of probabilistic and fluctuates whether it's likely to gain energy or likely to lose energy. So for systems like this, you need to think about the different possible macrostates the system could have, because sometimes it might have more energy than it started out with. Sometimes it might have a bit less. If it's allowed to exchange heat, it has the potential of getting some more energy and also the potential to lose some energy. So now you have to think about the possible macrostates it's allowed, because if it has more energy, it'll have a higher temperature overall. And these correspond to different macrostates. And each one, in turn, has a number of microstates. So there might be a macrostate which is more likely, which would correspond, you know, to the average temperature being equal to the average temperature inside being equal to the average temperature outside, and all of the gas molecules kind of having roughly the same kinetic energy that corresponds to that temperature. But you could have it differently. You could have a higher average kinetic energy, or you could have a higher total energy rather than your average kinetic energy. So you would still have the same temperature, but you could have different amounts of total energy in the system. And in that case, you have to sum over the different possible macrostates you have. And you get this very famous formula for the Gibbs entropy. So Pi here is the probability you're in a certain macrostate. And you sum over these probabilities. Well, P times log P. And this gives you a measure of the entropy of the system. Okay? But in general, we can think about entropy. We don't have to be too precise with it. We'll think about it as sort of the amount of ignorance we have about the system, or you can also still think of it in terms of the amount of disorder the system has. Either one is fine for our purposes, because we won't look into it in too much detail. Not really beyond a kind of thermodynamic understanding of entropy. Okay? So let's look at the two of the laws of thermodynamics that are going to be important to us. So there is the first law, which is really just a statement of conservation of energy. It says that the total internal energy of a system will change by the same amount as the heat that you add in, and then subtracting the work that the system does on its surroundings. So like if your system is, if you think of a balloon full of gas or something, you know, if it expands, it'll do work against the system you know, the external pressure that is pushing the walls of the balloon in. So it does work against that system. So it will lose energy actually if it expands, if its volume increases. So we have the energy gained by heat, which for a reversible process, I've just realized this is actually the wrong way around. That should be TDS, which for a reversible process is given by TDS. And we take away the energy that is given when the system expands or something, the work it does on the environment around it. And that is the total change in the energy, the internal energy of the system. So the first law of thermodynamics is really just a statement about conservation of energy. The second law is even more interesting, and this says that the total entropy of an isolated system always increases. So if you think about the universe as an isolated system, which is a pretty safe assumption, that means that the total energy of the universe will always increase. That is a law of physics. And this has a lot of consequences. And this appears when we'll talk about, more specifically about black holes, it appears that black holes violate this law. But actually we'll show in the end that that isn't the case, that they don't violate this law. Okay. So what about the macrostates of a black hole? So classically, a black hole is described by three numbers. It's described by its mass, its electromagnetic charge, and its angular momentum. And these are the only numbers that can describe a black hole. There's nothing else that can give you any more information about the black hole. I mean, aside from, things like its position, where it is, but nothing intrinsic about the black hole other than these things. And in fact, there's an equality that comes from just considering the Kerr metric. We won't go into exactly where this comes from, but in fact, a black hole can only form or can only exist when this inequality is satisfied. So here, J is the angular momentum, M is the mass, and Q is the total charge. You've always preferred your unrigorous interpretation of entropy as being kind of a reciprocal distance to equilibrium. Is that a good definition? I'm just trying to think that one through for myself. The unrigorous interpretation of entropy as being kind of a reciprocal distance to equilibrium. Yeah, I suppose so. I mean, like in equilibrium, you have maximum entropy. You have like the most number of microstates. So I suppose when you're close to equilibrium, you have higher entropy. When you're further away, you've got lower entropy. So I suppose, yeah, that's a nice definition, I think. Interesting. So I was saying that these three numbers alone, the mass, the charge, and the angular momentum, are the only things that can describe the state of a black hole. And this is formalized in the so-called no-hair theorem for black holes, which just says that there are no other possible numbers, no other pieces of information which describe the black hole, only these three numbers. There's nothing sort of interesting about the black hole's horizon. It's just, kind of a boundary. There's no hair on it, nothing you could do to distinguish one black hole from any other black hole other than their mass, their charge, and how much they're spinning, their angular momentum. Okay? But it's worth noting that this theorem is a completely classical result. Yeah, exactly. Contrasting the hairy ball theorem, which is a totally different thing. That's in topology, which I think I mentioned the other day, funnily enough. This just says that if you've got a sphere and you've got, if you imagine you've got hairs coming off of it, like a hairy ball, there's no way of combing the hair around it in such a way that doesn't like create a cowlick, like a discontinuity in the direction these hairs are going. But it's quite an unfortunate name, I think, for it. So yeah, this theorem is a classical GR result. It's not something you would expect to hold in a full theory of quantum gravity. And in fact, when we think about black hole microstates, which is something that is really still very uncertain and very speculative, string theory gives you a way to calculate the microstates of a black hole, or to count the microstates. But it's a little bit limited in that I think it only really works for black holes that carry a supersymmetric charge and are in higher dimensions. So as far as I know, I don't know if they've managed to reproduce exactly the Hawking-Bekenstein entropy formula. But it's still very promising, and it's interesting that it gives any sort of way to calculate any of these things related to the entropy of a black hole. And there are all sorts of things with holography where people are talking about entanglement entropy. But this stuff really, I have to sort of get my head around myself, actually. But it's all very interesting, and it's still a very open, very active area. So we've talked about black hole macrostates, which are purely described by mass charge and angular momentum. The microstates are much less clear what that would mean for a microstate of a black hole. Classically, it doesn't mean anything, because there is nothing there's no other degrees of freedom you have to describe the microstates of a black hole, because these three numbers are the only things that describe them. So classically, it doesn't seem like a black hole should have entropy. But, as we'll see in a minute, if a black hole doesn't have entropy, this seems to violate the second law of thermodynamics. So there appears to be a problem with the second law of thermodynamics and black holes. So if you imagine dropping a kind of parcel of entropy into a black hole. Now, what do we know about black holes? I mean, the most basic thing we know about black holes is that once stuff goes in, it doesn't come out. Classically, anyway, this is what we know. There's this horizon that once you pass through the horizon, you can't communicate any information, can't transmit any entropy or anything like that outside of the horizon, classically. So if you imagine dropping some source of entropy into the black hole, once it falls into the horizon, it's essentially lost to the rest of the universe. You know, there's no way of getting any information about it. If you didn't see it fall in, you would have no idea it was there. So if you hadn't seen it fall in, you couldn't possibly count it as a piece of entropy in the universe. So to an observer that hadn't seen it fall in, they could be totally justified in saying that the entropy in the universe had decreased, because we'd lost a piece of entropy into this black hole that you now can't measure, can't do anything with. So this seems to be a problem. Black holes seem to violate the second law of thermodynamics. The way this is fixed is by suggesting that a black hole has entropy. But how can a black hole have entropy? It seems so far what the no-hair theorem tells us is that a black hole is only described by three numbers. We don't know how to even begin thinking at this time about its microstates. So how can we possibly start thinking about its entropy? But actually there are some nice things you can do to start thinking about its entropy, because it turns out this is the only possible resolution. The only real resolution is that black holes do carry entropy. But where is this entropy carried? How is it described? How is it understood as a black hole? If the black hole is only described by three numbers, how do we understand the entropy of the black hole? So for this to be resolved, as I said, the black hole has to carry some entropy. And anything that has entropy to it, we know from classical thermodynamics, if it has entropy and it has some internal energy, it must have a temperature too. So we are now going to argue a particular value for the entropy of a black hole and for the temperature of a black hole after that. So this is a very, very cheaty derivation, which doesn't give you all the right factors. I mean, it gives you a surprisingly good estimate for the temperature of a black hole, or rather for the entropy of a black hole. But it does miss out. I think it's a factor of 2 pi or maybe 4 pi that it doesn't get out, that I couldn't find anywhere. I couldn't find anyone that gave a nice argument as to where you can get this 4 pi factor. I think it purely has to come from a more sophisticated argument. But this very simple argument, which I've seen given by Susskind and a few others, is very nice and very clear. So if you imagine we have a black hole here, and also this argument I think was originally done in a slightly different way by Bekenstein in deriving this entropy, in giving this estimate for the entropy of the black hole. But I think it was Hawking that came along and picked up this extra factor of 4 pi or something that will be missing. But anyway, this argument is very straight, it's very easy to follow, so it's quite nice. So if you have a black hole that I've drawn here, you can think about throwing matter into this black hole. And now we don't know how the black hole formed initially, and we don't really care how it got there from the beginning, but now it's there, we can think about throwing bits of information into it. So we're going to think about piling photons into it, which have got some wavelength, and we say that the wavelength of these photons that are being thrown into the black hole is roughly equal to the radius of the black hole. And this is just because if it was much bigger, then these things would not really interact with the black hole, they wouldn't really resolve them. And if it was a lot smaller, then the contribution wouldn't be as large. So it's a sort of order of magnitude. You say that the wavelength of the black hole is roughly equal to the wavelength of the particles you're throwing in, the light you're throwing in, is roughly equal to the radius of the black hole, as a sort of order of magnitude thing. These are the only real two length scales in the problem. So it's a kind of thing people often do, theorists often do, is set these length scales, say that they're approximately equal to each other. But it's a little cheaty, and it doesn't make complete sense to me if I'm totally honest, but this is the argument anyway. So if you throw in one of these photons, the photons are carrying an energy h bar omega, and omega is equal to the wave number times c, k times c, and k is equal to 1 over the wavelength. So this is h bar c over lambda is the energy of this photon that you're throwing in. And remember, we've said that lambda is on the same sort of scale as r, so this is hc over r, is the energy you're adding to the black hole for every one of these photons. So if you increase the energy of the black hole, you also increase the mass of the black hole. Clearly the wavelength should be r over 4 pi by the right answer theorem. That would be a good way of getting it, yeah, just saying, oh, you know, clearly as an exercise for the reader, the wavelength of the photon should be r over 4 pi. And then we get everything pi perfect, but I think I don't have the balls to make that claim, so I think I'll leave it as r. I mean, leaving it as r is kind of an assertion in itself enough. I wish I had the gall to set it to r over 4 pi. So if the energy of the black hole is increasing by this amount, then we can say, ooh, that's not a pen, that's a rubber. Just from E equals mc squared, which would relate the mass of the black hole, or the rest mass of the black hole, to the total energy of the black hole. That means that if the energy changes by this amount, the mass has got to change by this amount divided by c squared, which gives us now this c in the denominator. Okay, and then we've got from the Schwarzschild radius of the black hole, if the mass is changing by this amount, then that means that the radius is changing by this amount. So we have to multiply by 2g over c squared. But of course I already had a c on the bottom, so I pick up now a c cubed. So this is the change in the radius of the black hole by plopping this photon into it. And if its radius changes by this amount, well, you know the area of a sphere is 4 pi r squared. So therefore the change in area of the sphere when you change the radius is given by 8 pi r times dr. Okay. So if you put that in, you manage to find that the change in area is equal to this. And then if you kind of if you integrate this now, or if you change this delta A into the total area, if you imagine we've thrown in n of these photons, so some number n of these photons, that means that the total area you gain from throwing in all these photons is equal to this number 4gh over c cubed, where I've gone from, the reason I've lost some of these 8 pi's and stuff is because I've now rewritten h pi as h over 2 pi. So this is getting a little bit messy, but this is only the kind of very rough sketchy argument anyway. Then if you rearrange for n, the total number of bits, or well, the total number of photons you had to chuck in order to build the black hole up to this area, you get this formula here. And now again, we're being a little bit unclear in associating this with a number of bits. So the way I'm sort of arguing this is that, well, a photon has one piece of information you know about it, and that is its frequency, or its wavelength. So a photon only contains one piece of information. So if I've chucked in n of these photons of a particular wavelength, I've chucked in n bits of information into this black hole. And then we associate, again, rather haphazardly, and dropping a factor of k, which is important here. If you wanted to add it in, you'd have a factor kb here. We associate this information content of the black hole also with the entropy of the black hole. Okay, it's kind of quantizing our amount of ignorance. Well, no, sorry, not quantizing, quantifying our amount of ignorance we have about the black hole is all these bits of information that say you might not, you know, if someone hadn't been watching you throw in these photons, they would have no idea what the frequency of these photons were. So, you know, whatever information you chuck onto the black hole in the form of these photons is kind of preserved on it. So when someone comes along and looks at the black hole now, they would have to agree with you that it should contain that much information, the information content of the photons you chucked in. Where I'm again quite hand-wavingly arguing that this amount of information, because each photon has only one sort of important thing about it, which is its frequency, each photon is like a bit. And if you had to chuck in this many photons, that is the same as this many bits. And remarkably, this formula is very nearly correct. It's very nearly correct, but not quite. I think the way it's wrong is that this should be an h bar, so it's actually a factor of 2 pi out. And I can't spot where I've dropped to 2 pi, so I'm pretty sure that it just doesn't give the right answer. And I think this was an original problem that Bekenstein had too, that it took Hawking to come along with a slightly more sophisticated argument in order to give this factor of 2 pi that is important. But this factor of 2 pi doesn't come out of this argument we've given, because it's a very rough argument. A very, very rough argument. So we can do a bit better. We can give a slightly better argument for it to try and find the entropy of this black hole. Though actually, this is going about it in a different way. So instead now of trying to think about the entropy of the black hole, what I'm going to do is I'm going to try and think about the temperature of the black hole. And then from the temperature, I'm going to go back and figure out the entropy, because we'll know the total energy of the black hole, we'll know its temperature, and then we can figure out its entropy using some sort of basic thermodynamics. Okay. So this is another cheaty definition, derivation, but it's slightly less cheaty, but it's still very cheaty. Okay. And this really comes from an effect called the Unruh effect, which is a pretty cool effect that comes from quantum field theory and curved space-time, but as a sort of rough description of it, if you're accelerating through space-time, you'll actually sort of observe a thermal bath of particles, which depends on your acceleration surrounding you. And these particles, you know, this thermal bath wouldn't be observed by a stationary or non-accelerating observer. They'd only observed by the accelerating observer. So as a rough sketch of what we're going to do is I'm going to try and motivate this Unruh effect and derive it in a slightly cheeky way. And then we're going to think about the equivalence principle in general relativity, which says that accelerations and gravitational fields are really indistinguishable from one another, at least on sort of local scales anyway. So if we know the sort of thermal bath effect that is created by an acceleration, what I will then do is I will equate the gravitational field strength at the horizon of a black hole to a uniform acceleration, which is okay to do very locally in a very small patch of the horizon. And then I will say that the sort of effective acceleration you would have to produce in order to stay still just above the horizon, to not be taken away by the gravity, produces the thermal bath. And the thermal bath of this temperature is exactly the temperature given by the Unruh effect. And actually, when we do this, we do get exactly the right result for the Bekenstein-Hawking temperature. But it is done in a sneaky way. So it is not completely kosher, I will say right from the beginning. Okay? But let's try and get to it anyway, because it's quite a nice way of doing it. So yeah, we're going to try and convince ourselves through a slightly simplified argument that if you're accelerating in space-time, you observe this thermal bath of particles. Okay? So in order to do this, I'm going to consider the acceleration of a particle through space-time. So these are mu's here. I think someone commented on how terrible my mu's look before, which is very true. They do look very bad. So we define the proper acceleration of a particle as being the second derivative with respect to its proper time of its position coordinate. These proper things in special relativity are things you construct out of Lorentz invariant scalars. So you have a kind of Lorentz vector here, a 4 vector, and to keep it staying as a 4 vector on the left-hand side, I can only do things with it that involve Lorentz scalars or other Lorentz vectors. So the proper time is a Lorentz scalar. It's something that all observers will agree on for a given, for a given thing that is moving. They will all be able to agree on its proper time because it kind of is specific to that frame. So it sort of defines itself as being a Lorentz scalar. It's in a sort of slightly cheaty way. So we have a good definition for proper acceleration. This is a sort of Lorentz invariant version of acceleration. Okay. And if you take the position in space-time, which of course again involves a time coordinate and a spatial position coordinate. So when I put lines under things, I mean these are 3 vectors. These are ordinary spatial positions. But you know, in special relativity, we consider things, we consider space-time as this 4-dimensional manifold. So we have a time coordinate t, and we have 3 space coordinates that I underline with a bar. So what I want to get to is I want to get to this proper acceleration of the particle, which is this second derivative of its space-time coordinate with respect to its proper time. So in order to do that, I have to differentiate it twice with respect to the proper time. Okay. So when I do it once, this is, if you like, the proper velocity. It's the position with respect to the proper time, derivative with respect to the proper time. I get this expression here. That is gamma, the Lorentz factor, times c in the time component, and then v, the ordinary 3 velocity, as the space component. And if I do it again, I get a slightly uglier expression. So now I've got a factor of the rate of change in the gamma factor here. I've got here, this is the ordinary 3 acceleration, the normal space acceleration through space, and this is the ordinary velocity through space. But I've also got this gamma squared and this d gamma by d tau here. So these things complicate a little bit, but that's okay. So what I can do now is I can consider the magnitude of this 4 vector, of this proper acceleration. So, you know, to find the magnitude of this vector, you kind of contract it with itself. Or to think of it differently, I will take all of the time components squared and subtract them from all of these spatial components squared. So these ones here will be squared and added, and then all of these ones in the left bracket will be subtracted and squared, okay, because of this minus plus 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 metric signature in this non-Euclidean geometry you have in special relativity. And when I do this, when I evaluate all of this, of course, if I just do that for this expression here, I'll get something rather long and complicated. But what I'm free to do the power of this notation of writing things in terms of four vectors, in terms of Lorentz invariant vectors and scalars, is that the value of this contraction must be a Lorentz scalar, because it's a contraction of two Lorentz vectors. When you contract the two indices, the index goes away. It's no longer a vector. It's now, a dot product of the two, so it's a scalar. So this scalar must be the same in any reference frame. And if it's got to be the same in any reference frame, I'm free to evaluate it in any one convenient reference frame I'd like to choose. And then it's got to be the same in every one, even if it's a much less convenient, much uglier reference frame. It should still take the same kind of numerical value as it does in the simple reference frame. So what I choose to do is I choose to evaluate this magnitude here in the instantaneous co-moving reference frame of the particle that is accelerating itself. Okay, so the particle that is undergoing this particular proper acceleration, I think about, well, if you think about the motion of it through space, of its world line, if you were riding along next to it, instantaneously you would measure its velocity as 0, because you're moving alongside it. If you measure its velocity as 0, you measure the gamma factor as 1, and also instantaneously you would measure the change in its gamma factor as 0. So this factor here will also be 0. What is not 0 is the proper acceleration of this thing. Well, sorry, not the proper acceleration, the 3 acceleration that is measured instantaneously by you, because you would see this thing accelerating. You would see this particle speeding up even as you're moving alongside it. So I call this 3 acceleration A0. This is the acceleration measured in the particle's instantaneous co-moving reference frame. So from its perspective, how quickly does it think it's accelerating? And the magnitude of its 4 acceleration, this proper acceleration here, is equal to that. Okay. So now I kind of simplify, and I think about a particle moving in one dimension. So now its world line is just moving along an x-axis, but of course it's also evolving in time. It's moving in time. So its motion has a time direction and an x direction to it. So if I write down in component form what this 4 acceleration looks like, it's given by the second derivative with respect to tau of the time component and the second derivative with respect to tau of the space component. And if I wanted to write down its magnitude, again, remember, like I said before, with this minus plus 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 metric of Minkowski space, that would involve taking this component here, squaring it, and putting a minus in front of it, like I have here, and then adding that onto this component here squared. That is my metric choice. My metric choice is to have a plus for these components and a minus for this component here, for the time component. But other metric choices are available. Yeah, indeed, we are doing black hole thermodynamics. Nice to see you, Cosmolano. But this is the metric choice. I think I keep seeing loads of memes and lots of discussion on Twitter about people's favorite metric choices, whether they like plus, minus, 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 or minus, plus, plus, plus. I personally like minus, plus, plus, plus. I think plus, minus, 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 where you have negatives for all of the spatial components, I think that's generally favored by like high energy theorists. But I mean I am a high energy theorist, but I still prefer the minus, plus, 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 which I just think is a lot more natural. I mean, what, but I don't know. I mean, ultimately it's all the same thing. You might just get a minus sign somewhere where you didn't have one before, so it doesn't really make a difference. But I prefer minus, plus, 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 because it's like you're keeping time the same and space the time, sorry. And oh, you're plus. Oh, so you would put x, y, z, and then t. You would write t in the 4th position? Really? Huh. Okay. I mean, each to their own, I suppose. I like t as the 0 component. I think that's what you mean anyway by that notation. Correct me if I'm wrong, but no, I prefer the time as the 0 component, definitely. But anyway, in this metric convention, the proper acceleration, the magnitude of the proper acceleration becomes this first component minus and squared plus the second component just squared. Minus plus 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 when you're dealing with large spatial different distances, and plus minus minus when you're dealing with short distance scales. Yeah, I guess that's fair enough. Yeah, I suppose that's the idea behind it. I've never really thought about it in that way. That does make sense, but I don't know. I still like minus plus 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 for everything. And actually, in the papers I read, which I suppose are more like Het phenomenology or like GR quantum cosmology stuff, they tend to prefer like the minus plus plus plus. Maybe it's only hardcore HEP theory, they do other things. I'm not entirely sure. So what we've got here is we've evaluated the magnitude of the forward acceleration in terms of these 4-vector components. And we've also written it as being equal to this particular magnitude of the acceleration we found by considering or by thinking about what acceleration the observer would measure in their own instantaneous co-moving reference frame. Okay, so we've got this equation here. So this is actually an equation which describes the world lines of the particles moving through space-time. So here is the... Oh, what was that? Oh, thank you for following, Liddy36. So we have the time coordinate and the space coordinate of this particle as it moves along its world line, and we have the proper time that the observer or the particle moving would measure. Okay, so if we can solve these equations, what you have is you have a total parameterization or a total solution that tells you the world line of this particle, how the particle will actually move through space-time, okay, under this constant acceleration. So the solutions, which I'm just going to state, but you can check if you want to go and plug t tau into this derivative and x tau into this derivative, you get the right solution. You get that this all equals a naught, okay? You guess you meant tr equals minus plus, so yeah, minus plus plus plus. Why would I want more negatives floating around than needed? Yeah, I completely agree. But I think you're a GR person, aren't you, non-dairy neutrinos? So I guess your bias is clear in that respect. But yeah, I totally agree. That is my preferred metric convention too. Metric signature. So this is the solution that solves this equation here, for the world line of a particle that is accelerating in a uniform way. It measures its own acceleration as being a constant, this constant a naught, okay? Because the temporal duration between events is the more relevant part of your interval. Well, that's not always true, surely. I mean, it's all Bradley RL said the rules. I had to approve that because the auto mod said it shouldn't do it, but I thought it was too funny of a comment not to permit. Though it now means that I have added to the permitted term, so... Oh, I shouldn't have said that because now I'm going to have to try and filter it. Oh, I'll put a beep in later. If anyone wants to say go ahead and I'll just try and censor it. Anyway, so this is the equation of the world line of the particle. And we can find its velocity, or its proper velocity, that is the derivative of its position with respect to... well, actually, no, sorry, this is not the proper velocity. This is actually the velocity, the coordinate velocity of the particle. So the position, the free velocity you would measure as it moves through space-time. So if you were watching this particle accelerating away from you, this is the velocity you would measure it to have in your coordinate time. So dx dt, okay? You're glad you could cause chaos in the short amount of time you've been here. Well, it is appreciated. Thank you, Bradley. So to get this result here, that says that the velocity this thing moves off with as you would observe watching it go away from you is c tan h a naught t a naught tau over c. You just have to use the chain rule on this thing up here. So, you know, you would find dx d tau and you would find dt d tau and then use the chain rule to get dx dt. Okay, so this is the velocity of the particle as seen in the non-accelerating frame, in the rest frame. And what we can do now, there should be a over C there, is we can think about a particle that this observer would see, or think about some radiation that exists in this space-time. Now, the person that is accelerating in this reference frame, they will essentially see any radiation, any particles that are in this space-time Doppler shifted. Okay, and we can calculate the Doppler shift AC. So if this is the omega and k, the wave vector of the particle in as seen by us standing still, then the accelerating observer, the person that is zooming off away from us, they would see the same radiation, the same light, whatever it is, redshifted by this factor here. It will be Lorentz transformed. The wave vector will be Lorentz transformed. Okay. And for light, or for other massless things, we have that k is equal to omega over c, which will just pop up later on. We'll plug this in. Okay. So if I multiply these matrices, I get the two kind of Lorentz transformations for the frequency, what the frequency is observed of this radiation by the accelerating person will be, and what the wave number will be. But actually, because, you know, the wave number is really just the same as the frequency for something like light, which is what I'm considering here, it doesn't actually make a difference. These equations are just identical to one another. Okay. And also beta, this is nothing to do with thermodynamics, the beta here. This is not 1 over kt, this is v over c. So remember, because v is given by this, v over c is just tan h of this stuff in here. So the frequency of the radiation field is Doppler shifted. You know, it's either red shifted if you're moving away from it, or it's kind of blue shifted, it gets higher frequency if you're moving towards it. So this is if the radiation is going in the positive x direction away from you, in the same direction the person is accelerating in, then it's kind of red shifted by this exponential factor. And if it's moving away from you, it's kind of blue shifted if it's coming towards you as you're accelerating towards it. So this is like a sort of instantaneous, or like a time-dependent Doppler shift. So as you're accelerating, the red shift, you know, will get greater, and the blue shift will get greater the longer you're accelerating towards or away from this radiation field. Okay. So this produces waves with a time-dependent phase. Okay. So we started off with one wave, or one kind of matter that had a frequency omega. But now what happens is the frequency that is observed by the accelerating observer actually depends on the proper time that they have while they're moving along this world line. Okay. And the standard thing you want to do is, if you've got now a distribution which seems to contain multiple frequencies, which certainly this will if the frequency is changing with respect to time, in order to extract information about these frequencies you have, the standard trick is to take the Fourier transform. What this does is it tells you sort of how much of one frequency you've got compared to another. Okay, and we'll do this, and then we'll get from this the frequency spectrum. So the different frequencies that are present due to this Doppler shifting from this accelerating observer. So what frequencies of radiation they will observe. So we have this time-dependent angular frequency. And if I want to find the phase of this wave, so the phase usually you would say is omega times t, but because omega itself is a function of t, this is actually generalized so that now you take the integral with respect to t, or rather tau in this case. So now, well, that should also be a tau there, sorry. The phase of this wave is given by this expression here. We're doing this integral of omega, that should be a hat, of omega bar tau, brings down a factor of a, okay? So this is for us moving away from the radiation field, this example. Oh, sorry, no, this is for us moving towards the radiation field. No. This is for us moving, the radiation field coming, waves coming towards us and us moving into the waves. Sorry. That's the way round it is. Okay. And this is taking the Fourier transform of this wave. So we've got the wave that looks like e to the phi tau is our new phase of the wave that contains a mix of frequencies now that will depend on time in general. And we take the Fourier transform of it. So now I'm trying to see how many or what different amount of frequencies omega. So omega is kind of the frequency that I'm trying to see how much is contained. Wait, let me try and explain that again. So what you do with a Fourier transform is your Fourier transform is a function of frequency that I've called capital omega in this case. So I omega tells me of this wave packet here, roughly how much of the wave packet is made of waves with frequency capital omega. So it tells me how much of this total wave packet is dominated by waves with frequency capital omega. And it gives me an entire spectrum. So if the wave was purely made out, if I put a plane wave in here that was just, you know, e to the I omega or something, or, well, rather if I put like a, yeah, I mean, if I put a plane wave in which had one frequency, then this would just give me a delta function for the frequency at omega, and it will be 0 everywhere else. Okay, so the point is it's extracting information about what frequencies go in to this wave packet. Okay, so we have to do this integral to get the Fourier transform. And of course this looks like a little bit of a tricky integral. We've got an exponential times an exponential of an exponential. So a natural variable substitution to try is to try and get rid of this extra exponential up the top. So we try u equals e to the a naught tau over c. Okay, and then we just have to change all of these variables. We have to convert d tau into du, swap this out for a u, and then more or less it's pretty straightforward. We have to swap all of the taus out for t's, but other than that it's okay. And it actually turns our integral into something quite doable. It turns it into this integral here, where we have u to the power of some constant but potentially complex phase factor, and just times e to the I, some constant phase, times u. So this integral is actually a standard integral, which has a definite result. If you recall, if you've ever seen it before anyway, that the gamma function has this form here, that it's the integral over x times e to the minus x. Oh, no problem. See you later. Bye, non-dairy neutrino. The gamma function, remember, is defined in this way. So you can see that here it's like you've got x is swapped out for u, z is swapped out for this thing here, and we've got, well, here we've got an I instead of a minus x. But that's okay. This is just a phase that you could get rid of this, you know, by dividing the whole thing, by dividing u, redefining it as u times the I omega c over a naught. And then you would get rid of it up here, but you just pick up an extra factor down here. It doesn't do anything wrong, okay? And when you do it, you get this rather cumbersome looking result, which you've got a gamma factor of this phase we had up here, and all of this kind of nonsense, basically. But it's fine, it's just a number, this is now. Or rather, it's a distribution that tells us proportionately how much of any particular frequency we have in our new sort of Doppler-shifted radiation field. So as we're accelerating through the radiation field, we no longer just see a single frequency of radiation with, you know, frequency omega. What we now see is we see a distribution of frequencies. So we see lots of different frequencies, capital omega, that are given by this intensity distribution. Okay, well, maybe it's not intensity distribution actually. to get the real intensity, or the frequency spectrum of this thing, you actually have to do the modulus squared of it. Okay. So when you do the modulus squared of it, this gives us the frequency distribution of this radiation field that we see as we're accelerating through it. And you'll notice that quite incredibly, so first of all, I should say the gamma factor is just a number. It drops out. Taking the modulus of it, in fact, I think actually just gives you a constant factor, which is this factor here. But this is all from a table of integrals. It's not anything interesting, really. But the interesting thing is when you take the magnitude of this, you get this term here, which looks remarkably like the Planck distribution, which is the distribution of energies, you know, of a bosonic black body distribution. So something that doesn't have spin. In other words, you know, a perfect thermal black body. And if you compare this distribution, we get this factor here, sort of not bothering about the normalization and stuff. But if you compare this factor here with this 2 pi capital omega c over a naught to the form you expect from a Planck distribution, which here has a t in the denominator, by equating these two factors in the exponential, quite remarkably, you get the correct result for the Unruh temperature. The temperature you observe when you accelerate uniformly through a radiation field. Okay, you get this uniform temperature you would observe. Oh, Brewster asks, how much StatMech did you do at undergrad at this level? We did quite a lot of StatMech, I think, in my second year. So we definitely did, you know, stuff about microstates, macrostates, all these different distributions, and then, you know, like some quantum statistical mechanics, Fermi-Dirac and Bose-Einstein distributions. I'd say it's like it was part of the, it was quite a big part of the core curriculum we did in our second year. I think I think maybe it's more so of a core thing where we did it than I think at other places, but I don't know why. I mean, it's I really like it. I really like StatMech and thermodynamics, but you've done a bunch of theory about phase space and the states, but not a lot of the calculus to go alongside it. Okay. Do you think this implies the horizon has microstates? Ah, so we actually spoke a tiny bit about microstates earlier, only very vaguely, basically in just saying, well, so we talked about the macrostates first of all and said the macrostates are purely described as the mass, the charge, and the angular momentum by this no-hair theorem, which the no-hair theorem sort of says that there are no microstates, but the point is that you fully expect it to just be a classical GR theorem, and that actually in a full theory of quantum gravity, you would expect to find, you know, black holes with hair, black holes that have microstates. And in fact, string theory does give you a way to calculate or to count the microstates of black holes, but as far as I know, I think it's limited to black holes with supersymmetric charges on them and in higher than 4 dimensions. So to my knowledge, I don't think string theory has managed to produce the Bekenstein-Hawking entropy formula, you know, for an ordinary Schwarzschild black hole. But this is still something that is really open, and you know, I think certainly a black hole does have a description in terms of microstates, but I think, you know, you need a theory of quantum gravity to start calculating these microstates. But of course, string theory has managed to do that for certain types of black holes in certain kinds of string theory, but nothing, I think, nothing that exactly reproduces Hawking and Bekenstein's formula. As far as I know, maybe they have, but still, I suppose, you know, that's only good if string theory is good. I mean, if it turns out string theory is not the correct approach to be taking, then I guess the fact it happens to give this might just be another coincidence. But actually, the calculation for any kind of black hole of these microstates is an enormous success for string theory. So it is very encouraging, the fact that they've managed to calculate or to count the microstates of a black hole for some of these more exotic black holes. You can reproduce the formula with loop quantum gravity. Okay, I wasn't aware of that. I don't know much about loop quantum gravity at all. Um, but that's interesting. I mean, certainly you'd expect that these, you know, prospective quantum theories of gravity should be able to do this. You know, that's a test of them in a way that they should be able to reproduce this classical result, or semi-classical result anyway. But anyway, so in this kind of calculation, we have managed to argue something that looks remarkably similar to the Unruh effect. Again, we've done it in quite a cheeky way, but slightly less cheeky than the argument we did before. So what we've shown is that if you're accelerating through space-time, and you measure your own acceleration to be a0, so as you're accelerating, you yourself feel like you're accelerating at a rate of a0, as I've called it here, then you observe a kind of thermal temperature bath all around you that has this temperature given by the Unruh temperature, which we've managed to argue purely by thinking about special relativity with uniform for acceleration, and comparing this result, or Doppler shifting the frequency of the field you're moving through to give an effective temperature for a black body distribution, which is given by this Planck distribution up here. So we've shown that the frequency spectrum you get is actually equivalent to a Planck distribution, which has some temperature T. So we've managed to extract the temperature T of this black body radiation surrounding you from this factor here. So this is a kind of hand-wavy, slightly cheeky derivation of the Unruh temperature. So the Unruh temperature says that if you're accelerating through space-time, you feel a thermal bath around you that depends on your acceleration, okay? And what else do we know? So we're trying to apply this all to black holes. We have the equivalence principle in general relativity, which says that for all local experiments, the effects of gravity and the effects of acceleration are really indistinguishable from one another. You'd have no real way of knowing, if you were very, very tiny, on a very small scale anyway, whether you were accelerating in a uniform, if you were accelerating in space-time without any gravity around, or if you were in a gravitational field staying stationary. That is roughly what the equivalence principle says. So we should be able to use this to think about the gravity of a black hole, or the gravity around at the horizon of a black hole, in terms of acceleration. And if an acceleration produces a temperature, then by the equivalence principle, so too the gravity of the black hole should result in a temperature at the horizon. Okay, and that's how we'll try and apply this. So we need to think about what is the acceleration, or the effective acceleration, at the horizon of a black hole. How much would you have to accelerate by, pointing outwards to stay just above the horizon, to not get sucked in? And we're going to do this in an even more fudgy way. So now we're not even going to use GR to fudge this. We're just going to use normal Newtonian gravity to fudge it, because it gives the right number. And, if it gives the right number, what's the point in doing it a different way? Well, no, not literally. I don't really mean that. But for the sake of brevity, and for what we're doing at the moment, we'll do it with the Newtonian fudge. Okay. So if you imagine you've got a black hole with mass capital M, and, a small test mass or person with mass small m just on the outside of the horizon, where the horizon has got this radius RS, the Schwarzschild radius. So the force due to gravity from Newton is given by Newton's law of gravity, gmm over r squared, where r squared, the distance from the center of mass of the black hole to the person, is the Schwarzschild radius. Acceleration, from Newton's second law, is given by the force divided by the mass. So then we can say the kind of effective acceleration at the horizon is this gm over r squared we've got here. So will only stationary observers observe Hawking radiation? What do you mean? Do you mean stationary like to the event horizon? was so you would observe it even if you were, you know, very far away from the horizon, is the point. But that's interesting. Would you observe it if you were falling into the horizon? Because then I suppose, you know, if you're in free fall, you're locally in an inertial reference frame. So in that case, you wouldn't really have this. You wouldn't be in this uniformly accelerating frame. So the Unruh effect wouldn't quite apply there. So to my knowledge, I don't think you would actually see radiation produced if you were just falling into the black hole. And is that consistent with other things? So, if someone is outside seeing you fall in, they would see radiation coming out, and they would see you approaching the surface of the black hole, and sort of getting asymptotically close to it, but never actually passing through the horizon. Whereas you would pass through totally fine, but would see no radiation. Yeah, I don't think there's anything funny there. Something in my head doesn't quite feel right about that. It seems like there should be a slight contradiction you'd have to think about and resolve, but actually, maybe that's just fine. But yeah, that's my understanding, is that as you're uniformly falling in, I don't think you would observe Hawking radiation like that if you're in, you know, a free-falling reference frame falling in. I don't think so. I think you're right, yeah. So doing this Newtonian fudge, you get that the effective acceleration just outside of the horizon, or just on the horizon, is gm over r squared. And we know the radius of a black hole. We know the radius of the horizon in terms of the mass of the black hole. That is given by this Schwarzschild radius formula. So we can put this formula for Rs into the Rs here to get the kind of surface gravity, or the effective acceleration at the horizon of the black hole, which is this c to the fourth over 4gm. So putting this all together, we actually have the temperature of the black hole horizon. So we have the kind of Unruh temperature from this uniform acceleration, and we found that this uniform acceleration that is equivalent to the gravity at the black hole's surface, at least locally, produces this temperature h bar c cubed over 8 pi g mkb, which is exactly the result that Hawking got to for the temperature of a black hole. So we've got to the right result, but of course we've done it in a slightly cheeky way in several places. But it's pretty cool. It's a pretty cool result anyway, to show that black holes actually do have this thermal bath of radiation around them. They produce this temperature by this Hawking radiation, these particles that are emitted by the event horizon, or emitted, you know, from just outside of the event horizon anyway. Okay. But what we were initially talking about was entropy. So we've done it in a slightly backwards way. We've got temperature now, instead of where we had entropy before from doing this incredibly even fudgier argument. But now we've got temperature, and now for completeness I want to get entropy too, because that's also pretty cool. So we're going to use this classical thermodynamics result, du is equal to TdS. I think I wrote it down earlier, I think I wrote it was SDT, but it is definitely TdS. Or equivalently, T is equal to du by ds. You know, we're ignoring pressure and changes in volume. All of these things don't play a part. And then we're taking the internal energy of the black hole, the total energy of the black hole, to be given by its mass times c squared, just like we did earlier. Okay, that is the total energy of the black hole. It only depends on its mass, assuming it's not charged and has no angular momentum, as we are right now, just a normal Schwarzschild black hole. So then we can rearrange for ds for the entropy. ds will be c squared dm over t. So wait, is the temperature of the horizon or of the gravitation in general, as in does the Earth's gravitational field have a temperature? Yeah, no, I think this is a general thing. So I think the gravitation in general actually does sort of like induce a temperature kind of effect. It's just when it's very weak gravity, the effect is very weak. So there's not much coupling at all of these fields to gravity. But yeah, I think that's certainly true. Gravitation in general will affect the vacuum state of the particles that are all around popping in and out, and will kind of turn some of them into like a temperature field. It is pretty crazy, yeah. But of course, it's only really at a black hole that this plays a very important effect, where this gravity is very strong, that this effect becomes, quite a strong. Well, it's still not a strong effect. I mean, Hawking radiation is still very weak, but it's certainly stronger for black holes than for any other objects in the universe. So we've got ds, an expression for the entropy, and if we integrate 1 over T, 1 over the Hawking temperature we found before, with respect to mass, like this, you pick up an extra factor of 1/2 on the bottom, and you get an m squared up here when you integrate. You follow it all through, and then sort of anticipating the result, because we know what the entropy kind of should be, thanks to Bekenstein, that I think was the first to say that the entropy of a black hole should be associated with its surface area, because they share the property that neither one of them can decrease, classically anyway. Hawking showed that the area of a black hole can only increase, and the entropy, of the universe can also only increase. So if you lose a piece of entropy into the black hole, if you're looking for things about the black hole that should encode the entropy, the area was a good candidate for that, was what Bekenstein argued. But it wasn't until later he came up with the actual formula, I think incorrect up to a factor of 2 pi or something, and then Hawking came along later and fixed the factor of 2 pi using a more sophisticated analysis. So I anticipate this should have something to do with the area. So I kind of collect these 2gm over c squared terms that will give me the radius of the black hole, and I fudge some of these factors, well, not fudge them, rather. I correct for the ones I've taken into the square down here, I correct accordingly in putting ones in the denominator here. And then using that the radius is given by 2gm over c squared, we get this quite incredible result here, which is for the entropy of the black hole, which you can see is directly proportional to the area of the black hole. But in fact, it gets even nicer. There's an even more incredible way of writing this. So if you write things in terms of the Planck length, which is this fundamental length scale for quantum gravity, if you think about what are the constants that are important, for quantum mechanics, general relativity, special relativity, you've got the speed of light, you've got big G, Newton's constant, and you've got Planck's constant. Big G for gravity, h bar for quantum mechanics, c for speed of light. And then you think, what is the unique combination of these things I can put together that gives me a length scale? And the length scale it gives you is the Planck scale, which is, a very, very tiny length scale indeed. The fact that the horizon's area on 4 has always made me wonder, is the horizon's area or the shadow of the horizons that the entropy depends on? Oh, you mean, oh yeah, exactly, yeah, because, okay, so yeah, I'll get to that in a second. I know what you mean. So when I write the entropy in units of the Planck length, so this fundamental length scale for quantum gravity, if the fundamental length scale is LP, as I've written there, then a fundamental area scale is LP squared. So you can see I can collect this, this c cubed GH bar in here and rewrite this as A over 4 times the Planck length squared. So that's what Cosmolano is referring to. The fact that it's on over 4 is slightly unsatisfying, because it's not exactly, it's very nearly, the entropy of the black hole is very nearly just the area of the black hole measured in units of the Planck area, the fundamental area scale of quantum gravity. But it's not quite that, it's that divided by 4. So Cosmolano is saying, you wonder, is it the horizon's area or the shadow of the horizon that the entropy depends on? Yeah, I'm not sure. I don't know what it would mean, like the shadow of the horizon. Um, you know, I guess it's a numerical constant. Order 1 constants, it's fine. I mean, you know, uh, like the uncertainty principle is roughly correct whether you use h or h bar or h bar over 2 or h on 2. You know, all these order 1, 2 pi and whatever constants, they're not too important. But I agree that it's slightly unsatisfying. It would be a lot nicer if it was just a over lp squared. Um, yeah, I don't know. Maybe I'm not sure. Not sure. I think it's just the way it is. But it's an interesting thing to think about. But this is a really incredible result that Bekenstein and Hawking really were the two big names kind of coming to get this. And that is that roughly, if you measure the area of the event horizon of a black hole in units of the Planck length, then that gives you its entropy, which is pretty incredible. So actually, this saves the second law. Now, if you chuck a piece of entropy into a black hole, it no longer appears to violate the second law because you can't get any information out of the entropy that fell into the black hole. If you didn't see it fall in, you couldn't measure it. But now, because the entropy of a black hole can increase, now the information that falls in can be expressed as the entropy of the area. So you would have a way of measuring the entropy of the black hole. So all observers can agree that the second law is not violated, that entropy still increases in the universe overall. What you mean is that the area of the sphere is 4 times the area of a circle on the same radius, which you call the shadow. Oh, I see. Oh, okay. Yeah, I guess I see what you mean. So it's like that the area, instead of expressing the area of a sphere, you know, if you had it expressing... Oh wait, no, but surely it's the other way around. Like if it was 4 times A, then oh yeah, no, I'm being slow. Yeah, you're right. It is like the area of the 2D circle. You know, the cross section of the black hole. But I don't know. I think it's certainly thinking about it in terms of the 2D area, that is the area of the sphere, the 2 sphere, is the nice way to think about it. You know, this is where all these holographic arguments about black holes come from anyway, where the interior 3D, well, 3 spatial dimension part of the black hole is actually totally described by the 2D boundary part of the black hole, the horizon layer. That is sort of some, you know, the holographic interpretation of a black hole. But there are still problems with that. So something about I was reading something recently about a solution to... So if you chuck stuff into a black hole, so but the 4 is very suggestive in your opinion. Yeah, I don't know. Maybe. I'm not sure. To me, it just seems... I agree with what you're saying, that, you know, it looks like it might be... It would be nicer if it was just A over LP squared or something over LP squared. But to me, I think it's just a 4. I think it's still a very nice result with the 4. I'm not sure. I don't know if there's anything much more to it, but you know, it would be very interesting if there were. I'm not sure. So if thinking about the black hole kind of holographically, where all of the information that you chuck in is stored on the outside, there's a slight problem with this in that, you know, somebody that is falling in to the horizon, if they're falling into the black hole, from the perspective of people falling into the black hole, they pass the horizon with no difficulty. So they exist in the interior of the black hole. But from the perspective of somebody outside of the black hole, that information appears to be stored on the surface of the black hole. You know, when the black hole evaporates, that information disappears from the surface of it. It appears to all be stored on the horizon. And at a glance, this seems to violate an important theorem in quantum mechanics that is called the no-cloning theorem, that you can't exactly replicate, you know, information quantum mechanically, which you would have done if you had stuff existing in the bulk of the black hole on the interior, and also being represented on the exterior, on the horizon of the black hole. But I think a way someone has argued that you can get around this is if you just say, well, the person that fell into the black hole can never communicate with the person that is watching stuff fall in, that would interpret the entropy holographically on the outside of the black hole. So although there is a disagreement, there's no way either one of them can be informed of the other one's disagreement with them, which I think is roughly this idea of, I think it's called black hole complementarity, as a proposed solution to this problem. All this stuff is really fascinating. I really need to learn more about the sort of holographic side of black holes. But I'm quite excited because from next January I'm going to spend, hopefully, assuming no coronavirus and assuming the funding stuff goes okay, I'm going to spend 9 months at Berkeley next year working on this kind of holographic entanglement entropy stuff and holography to do with black holes. So I should learn a lot more about it then. But I need to learn a lot more about it before then too, actually, to prepare. Ah, hello, Matthew. Sorry you missed, but you're gonna watch the stream soon. Oh, no problem. Yeah, well, I mean, of course, it'll be saved and it'll be I'll put it on YouTube and stuff. You know, your worry about it is you don't know how to falsify it, as in you don't know how you would like prove it wrong. Yeah, it's a lot of these things to do with black holes kind of get a little philosophical in parts, or you know, it's really. Some of the thought experiments people do are very interesting, and how they figure all this stuff out. But yeah, all this stuff is still really all going on, and it's all very interesting. But yeah, I think that's more or less everything I wanted to talk about. Yeah, I'm curious as well. Do people prefer it when I do it like this, where I just kind of flick through the notes I've already written? If you want, by the way, for anyone that wasn't here, all of these notes I've been flicking through, there are on my website. So you can go and look at them. I have corrected some typos as I was going along. But some typos will still probably be there. But if you want to look through them, feel free to. What do I think about ER equals EPR? Yeah, that is also something I'm really not very sure about. I don't have a very developed opinion on it. Yeah. Yeah, it's I'm not sure what the current understanding of that is. What the current opinions and thoughts are on it. So I'm really not too sure if there's much I could say about it. But yeah, that stuff is interesting. I have a lot of homework to do. Well, not literal homework, as in I have a lot of homework in catching up and getting up to date with this stuff. But a really good book I like for some of this black hole stuff is I like this nice little book by Hawking and Lindsay. That's a great book. Quite brief, fairly, but you know, lots of interesting insights to it. And also this book by Frolov and Zelnikov on black hole physics. This is a nice book. So yeah, I've been reading through these quite a bit recently, only quite casually, I have to say, because I'm still not going to be working too much on this black hole stuff until next January, and I'm hoping to you know, try and publish something in a different area before then, more related to what my PhD research is on. So it's kind of on the back seat at the moment. But yeah, no, I really enjoy all this black hole stuff. I like talking about it too. I've been trying to think about what we could talk about on the next one of these. So the next, you know, one of these Saturday things. If anyone has any suggestions, that would be good. I mean, we could talk a little more about black holes. Oh yeah, actually yeah, both of the books I showed talk about black hole thermodynamics. Yeah, the Suskind one is sort of more, I guess, of an overview. It's slightly less strictly technical, whereas the Frolov and Zelnikov one is more like a textbook. It's quite technical and detailed, and gives you everything in full. But they're both really good books that I like quite a lot. And then there's also a really nice set of notes that I put on my Discord before. I think I sent them to Matchu, who was just in the chat. Which are these notes by Thomas Hartman from Cornell, and those are really good. If you just type in lectures on quantum, well, actually, I can probably send a link to them next time. ADS CFT. Well, I don't know about that. um, that might be a little ambitious. I actually posted a meme on Reddit the other day about ADS CFT that I was quite proud of. I mean, it was kind of silly. I don't know if I can get it up. Oh yeah, there on my Discord. Yeah, I posted the meme on my Discord too, but I found it funny because it was a format I hadn't seen much before. But yeah, actually, if you want to get the notes I was just talking about by Thomas Hartman, those are I really like those ones, Cosmolano, if you're interested. They go talk about a lot of ADS CFT stuff and black hole thermodynamics. So that's really interesting. Yeah, what was the other thing I was asking? Oh yeah, I was asking if do people like prefer it when I write things down as I go, or just when I kind of flick through stuff like this? Are either one of them fine, or like, does anyone have any preference? I don't know if anyone does, but I was just curious. Oh, you like the meme? Oh, nice. No problem. Yeah, I think they're in like one of the physics channels or something. I don't know. But yeah, potentially something to look at next weekend or the weekend after on Saturday. Maybe could be neutron stars in some more detail. I mean, we derived the equation of state for a white dwarf, like 2 weeks ago. Could maybe try and do the neutrons, an approximate one for a neutron star, though I think this is much more challenging because this thing is not exactly actually known, and you have to take into account general relativity when you're dealing with neutron stars, and looking for their equation of state. But that could be something interesting to talk about, or supernovae perhaps, something like that. I don't know. Maybe the flicking, because then you're able to be more attentive to what's going on with the chat. Not that you're not, but I think it would allow you to be a bit more. Okay, yeah, that's a good point actually. Yeah, because sometimes when I write stuff down, I do just kind of look down at the board. That's a good point. Yeah, I think I prefer it actually because it's just, I mean, it's kind of less pain for me having to write the same thing twice. So I can just kind of talk and it's a little more relaxed. So I tend to agree with you. But yeah, I don't know. Whatever. Writing for the derivation part. Okay. Maybe like that's a good point. Maybe like the blended version is best, where I could write the text stuff, so I could write all of this stuff here, and then just write down the stuff that is written there, but obviously it not being there, and then me filling it in as we go along. I guess that's kind of the best of both worlds. I think I had some lecturers that did that, which I found quite useful. So yeah, either one, either way, I think is pretty good. Well, yeah, so that was what I wanted to say about black holes for today. I'll have a think about what we could talk about next Saturday. But also in the meantime, so I also posted in my Discord that I made a Google form thing for the office hour questions, which is in like the main chat on the Discord. And I also put it on my Twitter. So if anyone wants to submit any questions that I could chat about, we could talk about on Tuesday, during the office hour, that would be cool, and I'd be interested to hear those. Do I care much for philosophy such as metaphysics or the philosophy of physics? Well, I'd say I have a passing interest in it. I'd say I don't know a lot of I don't read much about it, or don't study it. I don't read articles. I haven't really read any books on metaphysics or philosophy of physics, but I certainly think it's interesting. I like getting involved in these discussions, but I don't think I come from a particularly um, well-trained point of view in discussing them. Uh, it's nice to think about the deeper meaning of things, particularly in. I like thinking about the philosophy of how physics develops, the sort of logical chains of thought that lead to new developments, and how people come to these ideas, and how your bias tends to affect things. Like the idea of naturalness in physics is one that I've been thinking about lately, which still is funny to me. It's actually quite a big idea in physics at the moment that things should have this naturalness property, where they shouldn't be unnaturally large, unnaturally small, or particularly unnaturally fine-tuned. Um, and part of me, it's part of me just thinks, well, why shouldn't they be that way? Why is that so unnatural? Why should we desire our theories to be like that? But at the same time, I see the rationale. Um, but it seems funny to me. I think there's a lot more thinking I need to do there about why that is justified, why it is so desirable for theories to have this property of naturalness. So that's about as close to philosophy of physics as I get. Um, but yeah, sometimes it's nice to take a step back and think about that rather than just calculating things. But I prefer calculating things generally, so I don't think about it too much. Um, but yeah, I don't know. What about you? Do you like philosophy of physics? What kind of stuff do you read about it? Is what I mean. Natural means what exactly? Unusually large and small in reference to what? A set of physics. Well, yeah. So naturalness, I think it generally means like it's like comparative. So, for example, there's the hierarchy problem in particle physics, which is motivated by you would want things to be natural, in that um, the Planck scale is unnaturally large, as in energy scale. The Planck scale is unnaturally large compared to all other energy scales. It's a lot larger. So the way this is sort of fixed, or there are different ways you can fix this. One is uh, the way I'm interested in, the model I study is these higher dimensional models, where you have an additional fifth dimension that is kind of warped. Like a slice of ADS space, 5D ADS space, and this sort of redshifts your Planck scale. Well, it redshifts your 5D Planck scale and gives you the scale of like the electroweak scale, and redshifts all the masses of your particles so that they are you know on the scale they should be. But the Planck scale, the 4D Planck scale, is unaffected. So the scale at which quantum gravity becomes important is still very large, the energy scale. But it's explained in terms of parameters which don't require a great deal of fine tuning. So I suppose you could define naturalness as being where your theory doesn't require unnatural fine tuning. Um, okay, you're like me in that respect, yeah. So that's what I mean by naturalness, I think. Um, yeah. but it's not totally clear to me why that is the be all and end all. But I don't know. I'm not sure. It's interesting to think about, though. I do like thinking about those things. What is fine tuning? Well, it means like so for example, an example of a fine tuning problem is like in the present day, the temperature of the cosmic microwave background is very uniform. You know, it's all around 3 Kelvin or something, 3.7, or is it 2.7 Kelvin? I can't remember. It's very uniform, and temperature fluctuations are very tiny. I can't remember exactly how tiny they are, but they're very small. And if you were to explain this uniformness of the CMB today, without things like inflation, the 2.7, okay, right. What you would need to have in the very early universe, so just after the Big Bang, in order to have temperature fluctuations as they are today, maybe in the, well, I don't know, like 1,000th of a Kelvin or something. I don't actually know the exact number, but to have temperature fluctuations of around that scale, you would have to have temperature fluctuations within something like 1 in 10 to the, oh, I can't remember, 10 to the 30 or 10 to the 40 or something, some very large number in the very early universe, which means that if you had any slightly different variation in temperature in the very early universe, or fluctuations, you know, anisotropies, it would produce much, much larger fluctuations today. So it seems like it's very bizarre that the universe is fine-tuned in such a way that if you had a tiny, tiny change in this initial condition, you know, the temperature fluctuations in the very early universe, you would have enormous changes in, you know, the universe today. And that seems unnatural because, again, it relies on a very extreme fine-tuning. Things to be very precisely balanced early on, which I think is not something people are keen on. It seems unnatural that things should be like that. Another example is like the fine structure constant, I think, is an example of fine tuning. You know, if the fine structure constant that is related to the electromagnetic force was much different, then all sorts of things, all sorts of physics would be different, all sorts of chemistry, and then biochemistry, biology, and life would be very different if that was the case. So it seems unnatural that for such a small change, you would have such large consequences. Though I think actually maybe that's not a good example. I think the temperature fluctuations in the CMB is probably the better example, or the cosmological constant is another one, another example of fine tuning that seems unnatural. Yeah, it's an interesting notion, naturalness, and it's something physicists are pretty fond of at the moment. But I'd like to give it some more serious thought about the kind of philosophy of it, I suppose, why people are so keen on it. I mean, it roughly makes sense why people are keen on it. It does seem a little unnatural. Well, why is it unnatural? Well, that's what I mean. So this is the thing I need to think more about. Physicists call it unnatural because it's such a precise thing. If there was a tiny deviation, you know, to like 1 part in 10 to the 30, or it may even be something ridiculous like 10 to the 60, I can't remember, in the temperature fluctuations in the very early universe, there would be enormous differences today. Oh, why would they grow? Well, you know, because the universe has grown a lot since then, anisotropies tend to grow as the universe expands. So if you have sort of anisotropies or temperature fluctuations in the early universe, these would grow as the universe expands. So in order to have a pretty uniform CMB as we do today, you would have to have an extremely uniform temperature distribution with tiny, tiny fluctuations in the early universe. Which seems unnatural because, again, I keep using the word unnatural, but that is how people describe it. It seems unnatural that you would have these fluctuations as like 1 part in, again, I can't remember the number, 10 to the 60 maybe, 10 to the 40, I can't remember it. You'd have to work it out backwards from it. Yeah, so people aren't keen on that. And they want to try and find ways of getting around it or explaining these things without fine-tuning. Oh, I see. Oh, right. Are you saying that the illusion that the early universe was uniform is unnatural? Well, the idea that it's uniform to that extent is quite unnatural. Yeah. Well, I think fine-tuning of anything, again, I'm using the fact, the number 1 in 10 to the 60, which I think may be wrong, but it's something like that. It's some very large fine-tuning. I think for things to be fine-tuned to that extent, temperature fluctuations, in a way that's kind of ruled out by quantum mechanical effects. I think quantum mechanical effects, to my knowledge, would give you fluctuations larger than that. So it's almost like you couldn't even have things that uniform anyway. Things will naturally fluctuate, or rather, to stop them fluctuating to that extent that they are uniform to 1 part in 10 to the 60 would be almost impossible. It would be so I'm trying to say it without using the word unnatural, but it would be so carefully put together that it would be that close to uniform that it's very undesirable that things would be that way. So people aren't keen on it. And I suppose similar for the hierarchy problem. The difference between the Planck scale and the electroweak scale. That again we would expect to arise from. It's not perfectly uniform like the CMB. Exactly, it does have some fluctuations. That's what I mean. So it has fluctuations today, anisotropies that are something like, I don't know what it is, like 1 in 1,000 or something. But in order to have the size of the fluctuations you have today, you would have had to have had fluctuations of a much, much smaller size, like 1 in 10 to the whatever it is, 10 to the 60, 10 to the I don't know, in the early universe, very early on, which is very, very finely balanced, very finely tuned. Well, I don't know if it is. Yeah, I suppose. Well, it's that obviously we don't see more fluctuations, so that tells us that because we don't see those, you would expect even fewer in the very early universe. But the fact that you would have such a fine tuning of things in the very early universe seems unnatural, is what they mean by this. Yeah. Yeah, it is interesting. I'll have to think more about this. I did see an interesting paper somebody wrote about naturalness in physics. I can't remember who wrote it now. Let me see if I can find it. Because I should give it a read myself, actually. It was... Oh yeah, that was it. Actually, yeah, that was who it was by. It was by Sabine Hossenfelder. She wrote. There was an article I saw. Screams for explanation: fine-tuning and naturalness in the foundations of physics, which I kind of skimmed over, but I think I might reread it actually. If anyone's interested, I'll send the link to it here. Hopefully you can access that. I don't know if it'll open up right. But yeah, I think I'll read this evening. And if anybody else reads it and wants to chat about it, maybe we could talk about it on Monday. If anyone, you can just put in a thing in the Google form in my Discord and say if you want, then we could chat about it. But yeah, I think I'm going to take a look at this evening. Maybe not this evening, because I actually have some other work to do, but sometime before Tuesday. I think I said Monday. Yeah, Tuesday is office hour. Yeah. Do you need to have... You might need to have the Springer link thing. Okay, I definitely won't download it and put it in my Discord. No way would I do that. Okay. Oh, why did I just advance to level 1 in the disc? Oh, I don't know what that bot does yet. I need to sort that out. Anyway, yeah, okay. Well, yeah. So maybe I'll leave it there now. That was a really nice chat though. Thanks a lot, Cosmolano. I enjoyed that chat about naturalness and so on. That was great. But yeah, so I think I will leave the Saturday Spacewalk there for now. And if anyone has any suggestions about what they think maybe we could talk about next Saturday, then please do let me know. You could post it in the Discord or something. Speaking of which, there is my Discord again. And yeah, if you want to come along to office hour on Tuesday, then also in the Discord or on my Twitter, there's a Google form where you could put as many questions as you like if you have any, or just turn up and see what happens. I also tend to just flick through some physics memes while it's going on if no one's got questions. So we'll see how it goes. But yeah, I think I'll leave it there for now. So thanks a lot everyone for coming along. And hopefully see some of you on Tuesday, I guess. So yeah, thanks a lot. All right, see you guys soon. Okay, bye.